Hello students, welcome back to SapphireBlueChemspark. Let us start our today's session, the chapter D and F block elements. So already we have completed D block elements in our previous sessions. So we completed general characteristics of D block element and some important compounds of D block elements like potassium permanganate and potassium dichromate also. Now let us start the lanthanides and actinides. They belong to F block elements. Already we classified how these blocks are developed. Depends upon the last electron that enters into which of the subshell that makes their block. So in F block the valence electron, or we can say the differentiate electron that enters into either the 4f orbital or the 5f orbital. And 4f orbital, 5f orbital, those are anti-penultimate orbitals of the particular valence shell. And here the lanthanides and actinides, they belong to 6th period and 7th period. Already we discussed these lanthanides and actinides are the part of group number 3. In this first electron, when it enters into lanthanum, the d orbital, the next electron that will prefer to go to either n-4f orbital or to the 5f orbital of 6th period and the 7th period. So we are having the elements lanthanum. It has f orbital 0 but d orbital has 1 electron, followed by cerium to lutetium. In cerium to lutetium only, the f orbital is being filled progressively from 1 to 14 electrons. So after the fill up of the last element lutetium and lawrencium, once again the penultimate orbital, that is n-1 d orbital, being filled up. So the F block elements, they belong to 6th and 7th period and the group number is 3rd group, and their outer electronic configuration is n-2 f1 to 14, n-1 0 to 2. Depends upon their energies of n-2 orbital and n-1 d orbital, the electron that can be exchanged among themselves, and hence instead of writing d orbital 1 electron, we are writing 0 to 2 electron, and the ns orbital is being completely filled. So this ns orbital, we know the ultimate shell. These are the part of valence shell. In this valence shell, we have 3 types of orbitals. One is ultimate orbital, this is penultimate orbital, and the previous one is anti-penultimate orbital. So anti-penultimate orbital only the electron being filled up. That's why it is said to be inner orbital of that electronic configuration. And if at all the orbital 4f orbital is filled up, then the series is said to be 4f series. And the 4f series, that element begins with the lanthanum. That's why the name is given as lanthanides. So this series that includes lanthanum and cerium to lutetium. When we have 4f series, then I said this belong to 6th period. So where n equal to 6, substitute in this formula, you will get this electronic configuration for lanthanide series. n-2, n equal to 6, 6 minus 2 equal to 4, 6 minus 1 equal to 5, and 6s2. Similarly for actinides, where the differentiate electron enters into 5f orbital, that's why here n becomes equal to 7. Substitute in this general electronic configuration, we will get 5f 1 to 14, 60 0 to 2, 7s2. So these are their general outer electronic configuration of F block element. These two are the general electronic configuration of 4f series and 5f series. When we say about the position of F block elements, already I told they belong to group number 3 and period number 6 and 7. And these properties properties of elements are very close to the first member of series lanthanum and actinium. That's why they are termed as lanthanides and actinides, and their physical and chemical properties of those elements will be very close to each other. Physical and chemical properties of lanthanides. Actually, these elements, they are mostly metals and they are just lying below the periodic table. So on going down the group, most of the physical properties will be varied because that periodic table exhibits different properties in their different directions. So the properties of elements do not show the same trend both in period as well as in group. Let us discuss about physical and chemical properties of lanthanides. We know well, lanthanides and actinides are placed just below the periodic table. So their properties will also be changed according to their position. So let us see first of all the physical state. And these F block elements are mostly metal and hence they have silvery white shiny metals, but they possess low tensile strength. And being metal, they are good conductor of heat and electricity also. So when we compare the density is mass by volume. On going down the group, mass of the elements increases and hence density of lanthanides also increases. It ranges from 6.77 to 9.74 gram per centimeter cube. And the melting point and boiling point. The next one, melting point and boiling point. They possess fairly high melting point, but they do not show regular trend in their melting point as well as in boiling point. Then ionization enthalpy. This ionization enthalpy, actually it can able to exhibit +1, +2, +3 state. So the first ionization enthalpy and the second ionization enthalpy, that ranges from 600 kilojoule per mole to 1200 kilojoule per mole, and these values are very similar to that of the first group element and second group element, that is the S block element. That's why the properties of these elements are very close to that alkali metal as well as alkaline earth metals. So here we can say the lanthanum 3+, gadolinium 3+, lutetium 3+. They possess the empty 4f orbital, half filled 4f orbital and fully filled 4f orbital. So being their half filled, empty and fully filled, what happened? They possess very high ionization enthalpy in their +3 state, and moreover the electropositive character, that is also very high because of their very low ionization enthalpy. The next one, formation of colored ions. Just like D block transition elements, they do exhibit colored state in their solid form as well as in their solution. So when we discuss about the formation of colored ions, these are just like transition elements, exhibits color in their solid state as well as in their solution. In transition metals, we said that formation of color due to DD transition of electron. Here the electron is being transitioned from lower f orbital to higher f orbital, and moreover the empty, half filled, the empty and completely filled f orbital do not exhibit colored ions. The next one, magnetic behavior. Most of the lanthanides are paramagnetic in nature. This is why, because the 4f orbital is being progressively filled from 1 to 14. So most of the elements, they have their partially filled orbital and hence they exhibit paramagnetic behavior. But the elements which are having the empty 4f orbital or fully filled 4f orbital, they do exhibit diamagnetic character. So example, lanthanum 3+, cerium 4+, they have vacant empty orbital, 4f orbital, and ytterbium 2+ and lutetium 3+, they possess fully filled 4f orbital. So these ions are diamagnetic in nature. The next one, oxidation state, very important topic. In this, the lanthanides exhibits the most stable common oxidation state of +3. So whatever be the oxidation state of elements, they would tend to attain that plus 3 state only. So here they also exhibit plus 2 and plus 4 state. So I said the most stable common oxidation state of lanthanides is plus 3. Though they do exhibit plus 2 and plus 4, they tend to attain their plus 3 state only. That's why we can say the elements in plus 2 state behaves as a reducing agent and the elements in plus 4 state behaves as oxidizing agent. So when they do behave as an oxidizing agent, they can gain electron. So plus 4 changed into plus 3. Or when they behave as a reducing agent, they can lose the electron. So plus 2 can be changed into plus 3 state. So the most stable common oxidation state of lanthanides is plus 3. And lanthanum, gadolinium and lutetium. Lanthanum, it has the empty f orbital, 4f orbital. Gadolinium, it has a half filled 4f orbital, and lutetium, it has fully filled 4f orbital. That's why they are exceptionally stable besides that other elements. And we said the elements which are in lower oxidation state behaves as reducing agent, and the elements with the higher oxidation state exhibiting their behave as oxidizing agent. So like we can have some example, ceric ion Ce4 plus and terbium 4 plus. Both of them are in plus 4 state, so they will behave as very good oxidizing agent, and moreover ceric ion is a very good analytic reagent also. But europium 2 plus and samarium 2 plus, they do behave as a reducing agent. So the lower oxidation state reducing agent, they can change into plus 3 state, as well as the higher oxidation state, that will also the plus 4 state, tend to achieve their plus 3 state. The next property of lanthanides is atomic and ionic radii, the most important topic of lanthanides. So here they do not show regular trend in their atomic radii. There is no gradual decrease or even increase. But when we discuss about ionic radii, the size of plus 3 ion steadily decreases with the increase in atomic number. So the graph is plotted between the atomic number of lanthanides against their ionic radii. So we may find the graph, it shows deeply down the one. So the topmost element, they have very high atomic radii, but bottommost element, they become very low atomic radii. Why there is such a regular trend in their ionic radii? This is because of the electron that enters into 4f orbital. That 4f orbital, which has such a poor shielding effect compared to d orbital, p orbital and s orbital. Moreover, the electrons of f orbital is about 1 to 14. So whenever one electron enters into the 4f orbital, simultaneously one proton also enters into the nucleus. So the one side number of electron increases, the other side the number of protonic charge also increases. But because of the imperfect shielding of one 4f electron by another 4f electron, the increasing effective nuclear charge can cause the attraction of valence electron towards itself. Therefore, the electron cloud becomes shrink. That makes the regular decrease in the ionic radii of lanthanides. Such regular decrease in ionic radii with the increase in atomic number is said to be lanthanoid contraction. That is said to be lanthanoid contraction. So the cause for lanthanoid contraction is only we discussed because of the imperfect shielding of one 4f electron by another, and hence the increased effective nuclear charge attracts the valence shell more effectively. Therefore, there is a regular reduction in the size of ionic radii. Then what are the consequences of lanthanide contraction? The first consequences, because of the similar ionic radii and the second and third transition series of elements, they exhibit similar ionic and atomic radii and their properties also very close to each other. Already we said the zirconium and hafnium. Zirconium belongs to second transition series, hafnium belongs to third transition series. The zirconium and hafnium, they have very close atomic radii, about 160 picometer and 159 picometer. So due to lanthanide contraction, the second and third transition series of D block elements, they quite similar in their properties. The next one, separation of lanthanides. When these ions are very close to each other in their sizes, it is highly difficult to separate from their minerals. But even then, they do form complexes. But the formation of complexes by these elements greatly differ. So due to the difference in their complex formation, it is somewhat helpful to separate these ions from their mineral by ion exchange method. The next one, basic strength of hydroxides. So we are saying the ionic radii of lanthanides decreases. According to Fajan's rule, smaller the size of cation, larger the size of anion, covalent character increases. So here the ionic radii, that is the ionic size, decreases and hence the metal OH bond that possesses more covalent character. So we can say the lanthanum LaOH thrice, lanthanum hydroxide is more basic. But compared to lutetium, the last element, that becomes more acidic. This is because of the decrease in size of +3 ion that increases the covalent character in their metal hydroxide bond. That's all the consequences of lanthanide contraction. Very important topic. Always the question will be asked in your exams. Chemical reactivity of lanthanides. Already we said the ionization enthalpies of lanthanides are very close to the S block elements, 1s group as well as 2s group, and because of that the chemical property of lanthanides also very similar to the S block element. These lanthanide elements, they do react with non-metals as well as they liberate hydrogen from acids. So when it is heated with the carbon at 2773 Kelvin, it forms carbides. The carbides of various proportion, Ln3C or Ln2C3 or lanthanon C2 is given, where Ln that represents the entire elements. We are generally representing lanthanides as Ln. So on burning, combustion with the oxygen, they form oxides. So that oxides of the type is Ln2O3. Or when it is heated with the sulfur, they do form sulfides of the type Ln2S3. Or with the nitrogen on heating, they give nitrides, Ln, lanthanon nitrides. And also they react with the water, they do form hydroxides as well as hydrogen. And with the halogen, they form the halides of the type LnX3. Similarly, they do displace hydrogen from acids just like alkali and alkaline earth metals. So the property of lanthanides, which are very close to that S block elements only. S block elements also obey all these properties and forming their compounds. That's all. The lanthanides, we discussed about the position, physical property as well as chemical properties. The next one, actinides. So after lanthanides, when the differentiate electron enters into 5f orbital, they do form 5f series. This 5f series that belong to period number 7. And this period, that is almost composed of radioactive elements. Most all the elements are radioactive, but up to uranium, those elements are said to be transuranium element. Those are naturally occurring radioactive element. After uranium, they becomes artificially synthesized radioactive element. And these radioactive element, they possess very low half-life time. Half-life time is the time taken to reduce from 1 gram of the salt to its half gram is said to be half-life time. So most of the synthetic radioactive elements have very short-lived ones, and hence the chemistry of actinides become difficult. But we have the long-lived radioactive element also. Those are plutonium, uranium, thorium, neptunium. These and all, they have very long half-life. Compared to this, all other elements, that means the elements of the 7th period almost are composed of both naturally occurring radioactive element and the short-lived radioactive elements. Now, we can say that why the name actinides is given, because in 7th period under 3rd group, the first member of element is actinium, in which only the electron, that valence electron enters to it. After that, the other differentiate electrons and all entering into 5f orbital from thorium to lawrencium. That's why they constitute 5f series. And in this case, their general electronic configuration is 5f 1 2 14 60 0 to 1 or 2, sometimes it is 7s2. Then physical and chemical properties. Oxidation state, just like lanthanides, actinides also have the most stable oxidation state of +3 only. But lanthanides, they do exhibit only +2 or +4 state. But here these actinides exhibits the variable oxidation states that ranging from +2 to +7. And moreover, they can have the thorium plus ion, neptunium plus 7, plutonium plus 7. And we know well, the ones with the lower oxidation states are ionic, the ones with the higher oxidation states are covalent. So we can say thorium plus 4, that might be in ionic because of its lower oxidation state and can easily be hydrolyzed by water. But the others with the higher oxidation state +7, they become covalent in nature. The next one, physical state, just like lanthanides, these are also silvery white, but the surface of the metal becomes tarnished due to air oxidation. When the metal exposed to air, the surface will be slowly oxidized and hence it becomes tarnished. Density, on going down the group, we know well, mass of the atom elements increases and hence density also increases. So the 5f series elements have high density, but except those are thorium and americium, they have low density. Color, just like lanthanides, actinides also generally colored in nature, but the color of the ions depends upon the number of electrons present in 5f orbital. For example, uranium 3 plus is in red color and plutonium 3 plus is in blue color and americium 3 plus it is in pink color. The next one, ionization enthalpy. We know well, on going down the group, ionization enthalpy decreases because of the size of the ion or the element increases, and hence actinides, they possess very low ionization enthalpy. Electropositive character, because of very low ionization enthalpy, these elements are highly electropositive in nature. Melting point, boiling point, they do possess high melting and boiling point, but they do not exhibit any regular trend in their variation. Magnetic properties, actinides are paramagnetic, but when we try to explain about the paramagnetic behavior of actinides, it becomes more complex compared to lanthanides. Actinide contraction. Lanthanide contraction, that is because of 4f orbital whose shielding effect is very poor. Here the actinide contraction, it is because of 5f orbital. So we know the screening effect of orbitals are in the range of f orbital has very poor shielding effect. So we can write s orbital has the very high screening effect than p orbital, which is then d orbital, which is then f orbital. But when number of shell increases, that is the principal quantum number increases, the imperfect shielding also increases. So when we compare the shielding effect of 4f orbital to 5f orbital, the 5f orbital, it has still poor shielding effect compared to 4f orbital because of its more diffused shape. That's why it exhibits actinide contraction in their series. So there is also a regular decrease in the size of ions due to the imperfect shielding of 5f orbital is known as actinide contraction. Applications of F block elements. So here we are going to find out some applications of lanthanides and actinides. The first one is lanthanides, application of lanthanides, that is mish metal. The lanthanides are also known as rare earth elements. That means the occurrence of these elements on earth crust is very rare and hence they are named as rare earth elements. So in this mish metal, lanthanides are present about 94 to 95% along with 5% of iron. Also, it contains some traces of sulfur, carbon, silicon, calcium and aluminium. And these rare earth this mish metal, they contain cerium approximately to 40% and lanthanum and neodymium about 44% it is present. The mish metal, it is pyrophoric in nature. What do you mean by pyrophoric? Pyrophoric are the material that can spontaneously catches fire when it is exposed in air. So that's why it is used in lighters, flame throwing tanks as well as used to find out the tracer bullets and in shells. Then the mish metal, when it is allied with magnesium, that is used in making the some engine parts of jet. Then ceric sulfate is used as an oxidizing agent in volumetric analysis. Cerium salts are also used as catalyst in some of the reaction. And lanthanum trioxide, that is used in Crookes lens. It can protect from UV light. So these are some of the applications of lanthanides. When we say about actinides, the most of the elements are radioactive. So thorium, plutonium and uranium, these and all used as fuels in nuclear reactors. That's all the chapter D and F block elements. We completed the entire chapter, hoping that you will understand all the concepts whatever we discussed in our various sessions. Okay students, let us complete today's session and we will see in our next session with the new chapters, with the new informations. Until then, bye bye.